More NMR, more fun to be had. We're going to continue the discussion of shielding, try and wrap that up, and then introduce the concept of integration. Very useful information. All right, let's start where we left off. A quick recap from the previous mini lecture, which is basically about shielding and deshielding. So, nuclei, say a proton, a hydrogen, that all these hydrogens are in the exact same kind of electronic environment. Those are homotopic nuclei, and they will all have the exact same chemical shift. But if these nuclei, say hydrogens, are in slightly different electronic environments, they're called heterotopic, and they'll show up in different places in your proton NMR spectrum. They will have different chemical shifts. We wrap this all together by saying that deshielded nuclei up here to the left side of the NMR spectrum, that's downfield. That corresponds to absorbance at a higher frequency. Those little nuclei feel a bigger magnetic field and therefore a bigger energy gap. That means they show up at a larger part per million, a larger chemical shift. Whereas shielded nuclei, they're upfield on the right side of the spectrum. That's lower frequency, a smaller energy gap, smaller chemical shift. And that is the last mini lecture in a nutshell. But we left you hanging. What determines this whole shielding and deshielding thing? I kind of gave you a hint that's sort of like the clothing around the nuclei. Why is there even an effective magnetic field? Why are there heterotopic nuclei? There are three reasons why. 1, electronegativity. 2, the fact that we have methyl versus methylene versus methine hydrogens, and pi bonds, as we shall see. All right, let's look at electronegativity first. Let's look at this molecule. Let's see a little nomenclature-wise here. We've got a propane, a 1,2-dichloropropane. And what we can clearly see is that we have 3 different kinds of hydrogens. Now, what would we expect the proton NMR spectrum for this molecule to look like? If we focus on the methyl group first, then, according to our correlation chart, that signal for those 3 hydrogens on the methyl group should show up somewhere in the range of 0.9 to 1.0 parts per million. And as it happens, these show up just outside of that range, but in the general area, 1.2 parts per million. So that's one thing I can't stress enough, which is these are guesstimates and they're ranges. It doesn't mean they're going to show up all the way from 0.9 to 1. They show up typically somewhere in between 0.9 to 1 part per million. So there's a fudge factor built in here. These are just guidelines. All right, so that methyl group, according to our correlation chart, should show up around 1, and it actually shows up around 1.2. Now, what happens when I have a chlorine, an electronegative atom, attached to that CH2? All right, well, we know very well that chlorine is going to create a bond dipole there that's going to build up a slight positive charge on that carbon. And that means that carbon with the slight positive charge is going to be pulling a little bit of density, electron density away from that hydrogen, just slightly, ever so slightly. So it's removing that coat of electron density away from that carbon and that hydrogen. As a result, the chemical shift is pretty significantly impacted. So they're saying that a CH2 group that has a chlorine on that same carbon, the chemical shift is going to show up somewhere between 3.6 and 3.8. For this molecule, pretty close. It's around 3.4. So one lousy chlorine pulled that chemical shift for that CH2 all the way downfield to 3.4. That's a pretty big difference. All right, well, what about the last one? We've got a hydrogen on a carbon here that has an electronegative atom on it. I don't see, unfortunately, anything in my correlation chart that spells that out. So how do we figure this one out? Well, use your chart and figure it out. What you can see here is that as you go from a methyl group to a methylene to a methine, the chemical shift gets pulled further and further downfield. So if a CH2 with a chlorine on it is all the way down at around 3.4, then by extension a CH should be even further downfield, right? Because here, going from a CH2 to a CH, I'm going from 1.2 to 1.7 down to 1.5 to 2.0. It's going further downfield. So similarly, I should expect a methine here that has the chlorine attached to it to also be pulled further downfield. How much further downfield? I don't know. I'd say about 0.3 parts per million based on this comparison right here. So let's say it should be around 4.2 maybe? Yeah, pretty close. It's around, who knows? Maybe I didn't look it up. But it's somewhere around, I would expect that to show up somewhere around 4 to 4.2. So this example illustrates two aspects of electronegativity and the difference in a methylene versus a methine versus a methyl. We're going to look at lots of examples in this mini lecture. For example, this one. Okay, clearly in this NMR spectrum, I have two different kinds of signals. One here at 4 parts per million and one here at 7 to 8 parts per million. Well, this happens to be this molecule, methyl benzoate. What can we say about the chemical shifts here? Well, we have these different heterotopic nuclei, and clearly an electronegative atom in my oxygen. What we know is that we have a very polar bond here, pulling electron density, pulling the electron coat, the electron cloud away from that carbon, and therefore in turn away from those hydrogens, exposing them to the full brunt of the external magnetic field, de-shielding them compared to a regular methyl group that doesn't have the oxygen on it. Therefore, this is pulled downfield, de-shielded, and sure enough, it's exactly what we see. That it shows up right around where the correlation chart tells us it should, around 4 parts per million. It's worth pointing out here, yet again, these aromatic hydrogens, they're bizarre. Why are they all the way down here at 7 to 8? Well, it's certainly not electronegativity, so we'll have to come up with a different explanation for that. But the correlation chart does say, those things down there at 7 to 8, those have got to be these guys. All right, so electronegativity moves that coating of electron density around, de-shielding the adjacent nuclei and causing a downfield shift. The more electronegative, the greater the shift. The more electronegative atoms, similarly, the greater downfield shift. So in other words, if I have this versus this, well, this guy is going to be a lot further downfield than this guy with just one chlorine on that carbon. All right, so that was electronegativity. We've already looked at the CH3 versus CH2 versus CH impact, so the last thing we're going to look at is magnetic what? Well, magnetic anisotropy, of course. Magnetic anisotropy is that phenomenon associated with the pi bonds. So this explains the whole aromatic chemical shift. So this guy is a representation of benzene, and benzene of course has the 6 sp2 hybridized carbons, which means there are p orbitals on each one of these sp2 hybridized carbons. And those p orbitals overlap to give you this kind of donut-shaped thing. Basically what it shows you is that the electrons in the pi molecular orbital are all distributed equally all throughout the ring above and below the plane of the benzene. And when you put an aromatic compound like benzene in an external magnetic field, as shown, well, that generates the movement of these electrons in the little donut, and that in turn causes an internal magnetic field. In other words, those circulating pi electrons generates their own magnetic field, and when it does that, that's as signified by these blue lines. Well, here are my hydrogens sitting right here, and what do they feel? Ooh, boom. They are feeling, boom, an additional magnetic field, a magnetic field that's coming from the molecule itself. So it's reinforcing the external magnetic field. So what is this going to do? Well, external field is reinforced. That makes an even stronger external field. So remember how the energy gap gets bigger. These are really, really deshielded. And so that is why when we have an aromatic molecule with hydrogens on it, the signals for the aromatics always show up so far downfield. Here's another example. We've got something around 4. Bet you any money it's a OCH something, right? And then these guys, that's just screaming, 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 screaming aromatic hydrogens. But geez, what in the world could be even more deshielded? Well, your correlation chart will tell you in a heartbeat that that is associated with an aldehyde. Okay, so aldehydes show up. Oh, that's not associated with an aldehyde. Aldehydes are associated with around 9 parts per million. This is even further downfield, so your correlation chart is going to tell you that Nancy is wrong, that it's really associated with carboxylic acid. Hoo-wee, so that's really deshielded. All right, well, what about this other example? Let's see if we can make any sense of this. What do you do when you see this? NMR is absolutely positively overwhelming, and let me just remind you that there are lots of tutorials on the Canvas page that you should avail yourself of, including my helpful hints on how to get started. And the very first helpful hint I'm going to give you is that when you see this, if you're given the molecular formula, you are absolutely positively going to calculate the IHD. So what is the IHD for this molecule? C20? No, that's not right. No, I multiplied the number of hydrogens by 2. That's right. So for C10, that would translate into H24 plus 2 H26. If it's fully saturated, it should have 26 hydrogens. 26. It doesn't have 26 hydrogens. It only has 14. I mean, it only has 12, so it's missing 14 hydrogens. Well, if I divide that by 2, ooh-wee, 7? An IHD of 7? Is that even possible? Well, you know, it is, because when you look at an aromatic ring, that right there is an IHD of 4. So we clearly have a big number of missing hydrogens. And we clearly have an aromatic ring. So this is just kind of reviewing IHD and helping you see that we're obviously going to have to come up with some more double bonds or something like that. And we're not going to look at this particular spectrum in any more detail at this time. but I will just take a moment to point out there's lots more information here that we will get to eventually. First of all, notice this blue line, this is the integration. We will come to that. That tells us how many hydrogens are associated with this set of signals. And see how they've blown up these to show you their very clear patterns here. That's going to be even more down the road. That's called splitting. So for right now, what we can see is magnetic anisotropy has de-shielded these aromatic hydrogens and made them show up way downfield on the left. I can immediately say both of these have a benzene ring in them. A word of warning, there are certainly other aromatic functional groups besides benzene rings, but for now, that's a good guess. All right, now let's look at this set of examples to kind of hammer the point home here. C5H10O, it looks like that must have an IHD of 1 from these three isomeric examples, and I'll let you prove that to yourself. But let's look at a couple of proton NMR spectra here. All right, so here is the proton NMR spectra for one of these. Which one? Well, this is going to be all based on the chemical shift and the chemical shift only. I don't give you integrations, and we don't know anything about those patterns yet. So what I can see here in this one is, well, none of these are aromatic anyway, so that doesn't help me. But I do have a signal that is really far downfield. In fact, it's around 9, almost to 10. And if you'll remember in the previous previous example, I said something about aldehydes. So right off the bat, I'm going to say this has to be a match for that aldehyde, because neither this one nor this one would have a hydrogen that would show up with a chemical shift that far downfield. Not in a million years. So we rule those out. This has to be the aldehyde, and of course we could hammer that home in an instant with a good IR spectrum. We'd look for those nice fangs at 2750 and 2950 and a humongous carbonyl stretch at around 1715. Okay, so IR and NMR complement each other quite nicely. All right, well, how about this? This is another proton spectrum for a C5H10O. We've clearly already ruled out this guy. So does the one on the right match this guy or this guy? Well, it's a hell of a mess. But what you can see, you have an awful lot of signals between 5 and 6 parts per million. And if you look at your correlation chart, well, you shall see that that is exactly where alkene hydrogens show up. So, since I don't have any alkene hydrogens in that molecule, we're not going to say for sure that that is a match for the alcohol here. All right, last but not least, really not least, is integration. Integration is so easy to do and so useful, but so many people ignore it. Ignore it at your own peril. This is a spectrum obtained on our instrument downstairs, and what you see is a whole bunch of lines with numbers. So these little teeny lines here and these little numbers, those are your integrations. They look like integrals. That's why they're called integrations. And what that literally means is they are actually, the computer is calculating the area under each peak and associating it with the number of nuclei that gives rise to that signal. So it's really a simple measurement that basically allows you to say, oh, for this signal, that's 3 hydrogens. This signal, that's 4 hydrogens, and so on and so forth. However, I should note that these are relative numbers. All right, so I get an NMR, I have an integration, what do I do with it? Well, if you get an integration and you have no idea what your sample's molecular formula is, then you have to use the method of the least common denominator. So for example, let's say I have a spectrum where there's something like, look, this distance from here to here is 90 millimeters, and then this distance on the next integration is about 36, and then the next integration is about 34, and then there's one that's kind of in between. This distance is about 55. That's literally how an integration is measured, just from the bottom to the top. What does this mean in terms of number of nuclei giving rise to that signal? Well, you take the least common denominator, the lowest, the smallest number, 34, and divide everything by that smallest number. So you get the following, a ratio of 2.6 to 1 to 1 to 1.6, which of course makes zero sense whatsoever. Who has ever heard of a molecule that has 1.6 hydrogens? Nobody. So somehow or other I have to convert that into whole numbers, and if I multiply everything by 2, voila, I get roughly 5 to 2 to 2 to 3, and those are very sensible numbers. This could easily be a monosubstituted aromatic associated with a CH2 and a CH2 and a CH3. I'm not saying that's what it is, but it could be. Depends on the chemical shift, of course. All right, so that's one way you can do integration. If you do know the molecular formula, it's even easier. So for this molecule, C8H10, we can create a conversion factor. Basically, we know that there are 10 hydrogens in the molecule, and what we can see is that there are this many integration values. All I have to do is add them all up. 66 plus 26 plus 40. That is saying that 132 millimeters are associated with those 10 hydrogens. So 132 divided by 10 means there are 13.2 millimeters per hydrogen. Yay, a conversion factor. Now I can use dimensional analysis. If I multiply 66, or I should say divide 66 by my conversion factor, turns out 5 hydrogens. 26 divided by 13.2, 2 hydrogens. 40 divided by 13.2, 3. Easy peasy. So this is 5 hydrogens, 2 hydrogens, 3 hydrogens. Yay! And last but not least, when you get to be a whiz at NMR, you will start to recognize patterns. And that's, as I said, we'll get to splitting later. But basically, when you get to be an old hand at NMR, you'll recognize that this kind of pattern, a triplet in a quartet, is, as we like to say, bells and whistles for an ethyl group. So we will soon recognize that this is most likely a methyl group. This is most likely a CH2. And once you know that, and you know, for example, that this is a CH2, then you can figure out your other integrations from there. So we will go through boatloads and boatloads of examples and worksheets in class to help you with NMR. NMR is a practice kind of exercise, so we will do that in class.